for a wonderful chance to speak here. So it's a long story. It's a surprisingly, stubborn topic that just won't go away for about 30 years. So let me try to outline let A be an associative ring, or more generally, let's say a differential graded category, and M a bimodule, again a GG bimodule, or maybe an A infinity bimodule over A. Then it's classical from 1946 that there are chain and cochain complexes with coefficients in this bimodule. And so they have, first of all, they are explicit complexes given by explicit formulas, universal formulas. But second, they have an invariant homological or cohomological meaning. They compute X and Tor of A and M viewed as AA bimodules. This is one their feature, so to speak. On the other hand, they have this geometric intuition behind them. When A is commutative, there are maps, first of all, from the Hochschild complex with coefficients in itself. Yeah, maybe I should say that they are complexes, so they are equipped with differentials, which I think now are customary called B and delta, or maybe B and D. So there are also classical from the 60s morphisms of complexes, where differential forms are viewed as a complex if the differential is zero, so it has nothing to do so far with the RAM cohomology. And similarly, I think the best thing is to write it in another direction. Similarly for cohomology, where T is just the A module. In the commutative case, it's an A module of derivations of A. So on the spectrum of A, those are algebraic differential forms, and those are multivectors. And in good cases, actually, this is a quasi-isomorphism. But in any case, there are there is a whole class of operations, a rich algebraic structure coming from differential calculus. And here, of course, being coming from standard homological algebra, it has its own operations. Maybe I should mention a few. QNet formula or QNet product, Yoneda product, etc., etc. Cap. So there is some kind of dual provenance of operations that you expect on Hochschild and cyclic complexes, and that's probably why the subject is so non-trivial. And let me try to describe the future. Oh, I am sorry, the current state, and the current state, and then the future possible, developments. So what is known? And maybe it had been understood for a while that a good question to ask is not as much what is the full extent of operations, but rather what do DG categories form. And I believe that the question was asked by Drinfeld. There is a paper by Dima Tamarkin with this title, in some sense, I think, answering or reacting to this question. And that will be part of my story. But so let me describe one piece first. It's a key piece, and I think I would like to mention it. That there are, in the category of whatever it is, of differential graded categories, or simpler speaking, associative algebras, there are inner homomorphisms. So let me describe that. For any I mentioned them because in some sense they are a good definition of Hochschild cohomology. So given two differential graded categories A and B, there is a new differential graded category, which I will denote C of AB, and also I am kind of used to this dual sort of notation. I will also call it the DG category of A infinity functors from A to B. Why is that? Because its objects are, again, one can is representative enough if those are just algebras and those are morphisms of algebras, but better to think about they could be either DG functors or more generally A infinity functors. And then you have to describe morphisms. So probably let me try to put it upstairs. It will be just the Hochschild complex that I was mentioning above. of A as a ring with coefficients in B as a bimodule on which A acts on F from the left, or by F from the left, and by G from the right. Okay. I also have to describe the composition. It's some very simple explicit formula given by the cup product. It's actually the Yoneda product. So maybe it will become easier if I write, it computes, I am not saying that it's equal to, it computes R home in A bimodules of, I'm sorry, in AB bimodules of B on which B acts on the right and A acts on the left by F or by G accordingly. Then it would be just Yoneda product, but it's given by an explicit, very simple formula. Okay, so, and then so again, all Hochschild cohomological complexes, at least with coefficients in this type of bimodules, can be organized into such a GG category, and then it has a lot of key properties, namely, let me it behaves like home. It acts on A and works it into B, and it has composition. And I would say, first of all, there are actually not usual GG functors, but A infinity functors, and the good properties that one could expect, like associativity, are satisfied, but up to higher homotopies, I would say. So, in what sense, I will give a version below as a part of a more general structure. But this is the key. Again, this has a long history, and I think it starts with Getzler-Jones and Gerstenhaber-Voronov. And then also, I think, Lubashenko, Manzyuk, and Kontsevich-Soibelman, and the presentation that I probably, well, I won't follow here much in detail, but Bernard Keller has a good presentation and explanation of all this. But also in some other guises, I should mention other people like Bertrand Toye. Okay, so this is one piece of information. But this is only part of the story. Maybe I should stress that this is a rather practical thing. With Richard Nest, we arrived at it, not at this, at some cruder version of something kind of different, using some very, well, explicit calculations with something. And I guess my point is that it looks maybe complicated and will look even worse, but this is something to which it's a good idea to apply some functor like K-theory or cyclic homology and produce, calculate something and produce some explicit result about some characteristic classes or something. Okay, so next. So the classical fact is, of course, well, everything forms a category, of course, but algebras form a two category. Namely, as one morphisms, we could take just morphisms of them, but more generally, one could take bimodules. Then the composition becomes the tensor product, and two morphisms are morphisms of bimodule. In particular, an honest morphism of algebras does produce such a bimodule. Or maybe an A infinity morphism of algebras produces an A infinity bimodule. So one claim is that an analog of this is true in the derived, or I would say in a derived or higher sense. And again, this is by now a well-known statement. I am not even sure, well, definitely Jacob-Luria. It is contained in the results of Jacob-Luria, but I think there are many other versions of that. Maybe I should mention, I don't know, Batanin, Tamarkin. Probably there are many versions, but let me outline some specific version that I will be generalizing, and which definitely is contained. It's a partial case of Luria's structure. So let me say what I mean. One way let me start with one way of saying this. So what's a two category? It's a category in categories. I will relax appropriately the definition of category, make it category up to homotopy in the sense which I like for my needs. I could have done it here as well, but actually I don't need it. So you will see in a second what it is. So, namely, to any n categories arranged in order, I will associate a new differential graded category. Just to give you an idea where I am going, if I only have one arrow and two categories, and again, those arrows, they are abstract notions. Maybe I'm just saying that one follows. They're not actual morphisms. They are just, you know, well, the way of proceeding. So, for example, this, I am not saying that it will be equal to, but it will be quasi-isomorphic to this category that I had above. So I am in some sense building upon this inner home and generalizing it. So there are two types of operations. To any possible type of composition, I associate a DG functor. Let me just give you an example. If I have a chain of five DG categories, I can compose in two different ways, or rather in one way, but in two places, here and here. So a part of my data will be a collection of differential graded functors whenever I can compose. This is one piece of data. The other piece of data, I'm sorry, I will put it upstairs soon. The other piece of data is coproduct. I can cut my string in two, and yeah, so here they are, and define the coproduct for any such cutting. So my system of axioms is there are two sorts of operations, operations number one and operations number two, and they are all compatible in the most natural sense. The second one, for me, it's enough, just strictly co-associative. And the first ones agree in most natural way, and also the first one agrees with the second. I mean, the easiest system of axioms you can write about them, that's it. So this definition, this notion of an algebra up to homotopy is due to Thomas Leinster. And I think it works very well here. Maybe I should just say that in my case, I can define those explicitly, namely, I take those DG categories that I have there, take their bar constructions. Now they are all DG co-categories. tensor them, it's another GG co-category, and then take the cobar construction of that. That's it. That's the definition. One has to define those operations, number 1 and number 2. So let me just to give you a flavor that is straightforward. Number 1 comes from the Gessler. It's Gessler-Jones. They basically define this product at the level of bar constructions. There is a morphism, a DG functor of DG categories. You know, bar of that times bar of that to bar of the composition, and it is arranged. And number 2 is more or less tautological. It's kind of, I don't know, co-shuffle. Okay. And, well, like the claim is that it's immediate to verify that they satisfy those properties, all the properties that I need. Okay, so this is one way of saying that in some higher sense, differential graded categories form a 2 category. Let me try to say it in another way. Try to translate this in another language, maybe basically using this Leinster idea with coproducts, but I would say directly in the 2 category language and not like I did today. So in another way, and again it relates to works of Dima-Tamarkin and Batanin. So let me put it this way. You consider such a figure. I don't know, a banana bunch or where those are now algebras, and those are morphisms, so they are not or infinity morphisms. They are not some, you know, abstract arrows that indicate directions. They are actually infinity functors from one DG category to another. So, to any, let's call it for I don't know, let's call it a figure. To any figure, we associate such a complex, a chain complex. Probably it follows from there what you associate to it. I think when I will be generalizing, I will say what it is. But it's kind of, it's prescribed there. What maybe you know what, since this thing I would like to keep on the blackboard. Maybe, can everybody see here? So, is the figure, if the figure 2 is obtained by the figure from the figure 1 by two types of operations, namely, one can delete a horizontal arrow, so like this, or one can delete the maybe let me try to if you have this, basically I want to remove the arrow and to, well, to make them just lines, but I have to deal with the fact that there are more incoming here than outgoing here. So in this case, they should share. So let me so I can do this to my figure. So this corresponds, of course, to vertical and horizontal compositions. Then I must have these will be morphisms of the first type. And then there also should be a co-multiplication, co-associative in the most straightforward way, where maybe let me write it here by I won't, you know, go into let me say that either this is my possibility, or perhaps this is my possibility. And they all agree with each other in the most natural way. Okay, so this is another way of saying that GG categories form a two-category up to homotopy. Okay, but now, yeah, maybe I should also say maybe I should say that the usual two category you have basically for every, and let me start for every elementary banana you have a complex, and then there are two sorts of compositions. And here they are, vertical and horizontal. And in this case, C of the figure is just the tensor product of all C of elementary parts. Okay, so this is the usual two category. Maybe also I would like to mention chains. I won't have much time, but at least for a few minutes, I'd like to mention chains. There is actually one subtlety there, namely, so again, maybe so let me recall that this is my elementary block, and also is it easy to erase if I use colored chalk? Do you know? Yeah, I think it's fine. I can consider chains with coefficients in the same bimodule, and it will be another complex. So now I have this two-colored situation, and again, naively, when I try to do some elementary operations, first of all, let me with respect to the cup product, the Yoneda kind of part, it's just straightforward that the chains are a bimodule. You can multiply from left and from the right. So you have this operation. And then you would expect that chains form a bimodule over cochains with respect to kind of all possible, in any case, imaginable. So you would expect this operation and a similar operation in the other direction. But it gets kind of twisted, namely, well, I don't even know how to explain it in words, but this is the second operation that we get. But again, if you take it into account, then in the same spirit, you can show that chains and cochains form to something. I don't even know how to say this. I think, well, so some provisional definition is a dimodule instead of a bimodule, or maybe it's a bimodule vertically and a dimodule horizontally. It's kind of okay. So yes, now maybe let me also spend a few minutes talking about the plan that I would like to pursue. What's the standard by now way of thought? you have this. You somehow establish the result that DG categories form a two-category up to homotopy. From here, you conclude that it has, in some correct sense, two commuting E1 structures, where E1 are little intervals, and because of that, whatever you do, you probably are somehow using this picture. E1 times E1 is E2. So you arrive at the fact that the Hochschild cochains form an algebra over little disks, chain complexes of little disks, or little rectangles in this case, which used to be the Deligne conjecture. And you also do you can also do a similar thing for chains. And then following Kamarkin and then other proofs, Kontsevich, you argue that this operad is actually formal, and therefore the Hochschild cochains and chains you can include, they are an algebra over an operad of much more calculus nature. There are same types of operations and same types of relations as in the standard calculus of chains and cochains. Okay, so this is the line of thought that I would like to generalize, and I guess I am barely at the very top of that. So let me start and finish basically by explaining that. So let us look at this picture and notice that there are other operations as well. It's not just let me draw a more general space, something like So it's a bipartite graph. I think the correct way of saying it is not to put it on the plane, but to say that it's a bipartite graph where not only vertices are of two types, but also arrows are of two types, left and right. The valency of each vertex is 2, one left and one right. So it's a completely self-dual notion. You can replace vertices by arrows and so on. What does it correspond to? Well, such a thing corresponds to if you put an algebra into every node, and the morphism or an a infinity functor into every arrow. Maybe again, let me make it part of the definition that then you can form a complex, namely Hochschild cochains of the tensor product of those algebras with coefficients in those algebras on which this acts as is prescribed by this picture. Namely, well, for example, A1 acts on B1 here and on B3 here. Or am I F1R? And similarly for chains. So why? So let me just say that those things seem to arise naturally in basic, in a lot of questions of non-commutative geometry. For example, when you study Calabi-Yau algebras and I will mention it, by the way, Calabi-Yau algebras and categories in their different guises. Also, behavior of those invariants under Morita equivalence. And I was always perplexed very much that I described somewhere, well, I erased it, this, you know, what I call non-commutative differential calculus. And there is this very long road from the two category to it. But there are other formulas and methods and calculations due, for example, to Ginzburg and Vandenberg and others, also of this calculus provenance, but very much different. And I was always perplexed, why is this, how to put it into a... So maybe I should also say that in case when all AI are the same and all Fi are just identities, what you get there is the Hochschild complex of A tensor n with coefficients in A tensor n. But this A tensor n acts, it's an algebra, it acts on itself on the left trivially, I mean not trivially, but through the identity morphism, and on the right through the cyclic permutation. So let's keep this in mind. And I heard from Maxim Kontsevich some sort, I wouldn't call it a conjecture, maybe in his mind it was a conjecture, but I don't know, at least a question what should those things satisfy. But I can't recall now. I mean, well, it's, but let's keep in mind that there are those. Let's keep in mind also that the corresponding chain complexes they are just the usual Hochschild homology. So in particular, if we kind of figure out all those new structures, we will get a lot more module structure, a lot more of a module structure on the standard Hochschild chain complex. Okay, so what is known? There are two types of compositions, same as before, and maybe let me give you an example. Something's wrong here. If you have this, you can just, as before, you can cross this and you will get and you have this. Maybe let me so basically, without those intricacies, it's just this and this. which satisfy again all the associativities and congruences with each other that you can imagine. So maybe I should, well, so I don't even have a name for it, but let me just say that there is this structure up to homotopy on DG categories in the same, exactly in the same sense as there. Exactly in the same sense as there. The only thing that I probably have to say is and again, it's probably lack of my fantasy and probably not the final version, but so far this feature that you join several things by just by their end points, this remains, but it could be subdivided in some non-trivial way. I don't know. Okay, maybe last thing that I would like to say. First of all, the proof, if I just look at the thing with bar co-bar that I described and just try to decipher it, it works very well in this setup. There are explicit formulas, and it all works very well. Sort of Boardman-Vogt argument. The only thing as in the usual calculus of Hochschild cochains, there is a generalized Gerstenhaber bracket. It just, for n equal 1, it's the Gerstenhaber bracket. And there is, I saw notes of a talk by Kontsevich, and I think it's joined Kontsevich-Vlasopoulos, where basically they give a definition that a weak Calabi-Yau structure on A is by definition a Maurer-Cartan element of this DGLA. So I can't say much more, and so you see, for example, this long road from two categories all the way down that I erased. Somewhere there was a there was the fact that there is a DG Lie algebra structure, or at least the Hochschild cohomology is a graded Lie algebra. Why do we know that? Because we know that it's an algebra over little disks, and the operad of little disks has a Lie bracket in it. So here I am not even at this stage. Well, I am at the very top stage, and probably in a very imperfect version. So I can't tell anything more, but okay, thank you very much.
It's a shot in the dark, really. I trying to understand. So when you have your DG categories or algebras arranged in a linear order, so there is another one you can associate to it. So what about the? I mean, before you even go to dimensional, what about some other configurations, like when you have a tree with edges labeled by DG categories? Associate another one to such a configuration.
I think a good way that I know of saying it is that, well, to any graph, maybe one way, this thing with the linear order, I don't like because it's not symmetric. You don't get a symmetric monoidal category here. You have this order. So maybe better to have not a tree, you are absolutely right, but any graph. But any graph. And if you have a graph of algebras, then there is some way of getting a composition and obtaining another graph. For example, instead of those two, you can do this. Instead of those two, you can do this, and I don't know, whatever. So this will be another graph. So maybe this is better. It's a little bit more cumbersome. This is why I didn't use it here, but you are right. I think it's better. It's more invariant, symmetric, etc.
So I understand that from your two category you get the Gerstner algebra and the Hochschild cohomology.
Yes.
But the full calculus, how do you see this coming just from the two category structure?
No. You have to use two category plus this whatever by die module on cochains and chains. You need a statement of an algebra over two colored operads on chains and cochains. By the way, it's in some sense it's obvious in retrospect that you get something less naive than just a by module, because then you would get some naive version of a Gersten-Haber bimodule on forms, which is not the case. It's kind of a twisted Gersten-Haber bimodule.
Sorry, can the Gersten-Haber composition product be seen in this language of diagrams?
Gersten-Haber composition product, sort of the brace. In the language of diagrams, these are all secondary operations, you know, as every higher structure, it has the primary operations, then you expect to get something, some equations, and then you only get them up to homotopy. And as part of those homotopies, you get those braces, and for example, the cyclic differential capital B is on the same nature. It's a very cute exercise that I didn't know till recently how to obtain the cyclic differential capital B in this respect. But there are some things like the capital B and the Gerstenhaber bracket that you can explain in some sense invariantly. Yes, that they must be there. But one-sided brace, I am not sure. It's maybe, I don't know.
So is it possible to obtain such operations on other for other resolutions rather than the standard one? I mean, you have explained that Hochschild homology, they're just torsion and extension functors, so you can plug in arbitrary resolution there. And I wonder if you can obtain similar operations for arbitrary resolutions.
I mean, the answer, from my experience, probably yes. And again, I remember this way, I mean, 30 years ago, probably I tried this for this cyclic capital B and for the Gerstenhaber bracket, and the answer was yes. But all this in full generality, I would probably think yes, but I don't know. And maybe for some resolutions it's kind of more natural.
Time to speak again.